Yeah, I mean, there are many ways of doing a course like this, as I've probably mentioned. The canonical way in which non-equilibrium uh, StatMech or you know StatMech slash dynamics in condensed matter is done is by starting with rate equations and uh, Brownian type problems, which are very general purpose tools, very versatile tools. Moving on to how to do linear response theory, which is what we are really doing in much more depth than usual. Usual meaning in such a course, and then some shade of experiments and how things are done. My goal is a little different because that kind of material you will find in many, not many, but several of the books that are around on the topic. One of the books being the book by V. Balakrishnan that Vivek knows. Uh, Tony, I don't know if I mentioned this to you. Um, did I mention Balakrishnan's book?
No.
Okay, so this that book is it's a nice book. It's called Elements of Non-Equilibrium Statistical Mechanics. That's the book that Vivek is showing you. That book. There is a Springer version of it, and this is the Indian edition. The Springer version looks a little different, but I also have the Indian edition myself. Uh, it's a very handy book because the name is Balakrishnan, Balakrishnan, V. Balakrishnan, Elements of Non-Equilibrium Statistical Mechanics. Now, the reason why I mention this book is because um, it's a very sort of decent book. It is not very complete, but it's a very decent book, and it has a pretty good collection of these chapters, these canonical chapters that I mentioned to you. Um, and it is very readable at some level. The problem with the book is it is a little jumpy. So it'll tell you, uh, an important step in getting to a result, but then without going through about 5 or 7 important steps, it jumps to the result. I find it a little jumpy. And that can be very distracting because then you spend hours and hours trying to figure out how you got from there to here. That's the main limitation of the book, but that is true of most books. The reason why the book is nevertheless very useful is because you could actually go online on YouTube and find Balakrishnan's lectures, which are taken uh, from the course that led to this book. So therefore, you have a very good um, link between those lectures and the material in the book. And in his lectures, he's extremely good. I mean, he's one of India's topmost lecturers in terms of communicating material to students, and very, very decent lecturer. So I very strongly recommend, looking at that stuff if you find a little bit of time to explore and having it around with you, either in a PDF format or in a hard copy format. If you want, Vivek can probably get that book and send it to you by by mail from India, which would be much cheaper than buying it from Springer. It'll probably go about $15 level. Buying it from Springer will set you back quite a bit. Um, anyway, there are other books also, like Balakrishnan's book, which are a little bit more formal. We talked about the book by Robert Swanzig, Zwanzig, uh, called Non-Equilibrium Statistical Mechanics. That's also a very solid book, very nicely written, very rigorous, mathematically quite nicely done. Formal though, it's not really. uh, a light read, but it's a good book. These two books are very nice, and I strongly, uh, suggest that when you find a chance, get a hold of these books and kind of keep them around because it'll tie you back to the material we have discussed, which of course I'm giving you anyway. Now, we talked about the fact that in addition to the spin systems we have looked at in one dimension and higher dimensions are of course very difficult to do, but one can try them. There are some works in higher dimension spin systems. The next big basic set of systems are the uh, lattice systems. And in lattice systems, once again, we return to one dimension as the starting point and pretty much remain there because what most people don't learn in the course of their graduate school and even later in life is that lattice systems are incredibly challenging, and we actually don't even have a theory of how three-dimensional or a two-dimensional lattice melts, which is in any way rigorous. We don't. We have long wavelength theories of two-dimensional melting, which led to, part of a Nobel Prize. This was the Nobel Prize by Kosterlitz and Thouless um, on topological melting and stuff like that. But this is basically the story of the melting of a simple two-dimensional lattice. Okay? That's how uh, that's how difficult this topic is. Um, can you study such a topic from an atomistic scale like we are doing? The short answer is you probably can, but the mathematical challenges are pretty insurmountable even today, such that nobody has attempted it. So there is no real attempt to understand uh, theoretically the lattice scale uh, properties as a two-dimensional lattice melts. Uh, one can simulate that, and one can do a long wavelength theory, which basically means that if you know the answer of what to expect, you build it into an elasticity theory Hamiltonian, something that we physicists don't typically learn, at least in the United States, and essentially carve out from it a theory that was done in 1975 through 1980 timeframe by several people in the US, and uh, the formal theory was set up by Bert Halperin and David Nelson out of Harvard, and at University of California, Santa Cruz, uh, Peter Young, a British theorist, constructed independently a very similar model. And then Kosterlitz and Thouless developed their ideas in a little earlier. They were much more limited in scope. They are the ones who got the Nobel Prize. And apparently, in the 1960s, a Russian theorist by the name Berezin, Berezin, Berezin actually developed the first version of this theory that was much later kind of observed, and Berezin was given credit as well. So it was Berezin, Kosterlitz and Thouless, and then Halperin and Nelson and Young. So it's called BKT-HNY theory. So in 2D, it is the BKT-HNY theory that describes melting. In 1D, of course, uh, things are not very stable actually. So if you take a lattice and if you excite it, then this lattice can easily start to fall apart. It can easily basically become a liquid um, in the presence of thermal vibrations, which we don't consider here. So in the presence of thermal vibrations, it can easily become a liquid, and therefore we study lattices essentially at zero temperature for that reason, such that they're more or less frozen. Okay. So these physical concepts are very important because ultimately what we are doing uh, is whatever system building we are doing, we are going to try to relate it to experiment at some level or another. If your theory has no connection with experiment, then you have to take a call on whether you want to pay attention to the theory. In my book, that is not worth spending much time on, unless there is a hope that it might connect with experiment. Because you don't know. I mean, nature is quite uh, nature loves to play games with you. So if you want to fall for it, you can go for it. Okay. But if you want to stay straight and do your sort of job of being a scientist, then you have to think like a scientist as to what checks out and where nature intentionally took you in the wrong way. Okay. So it's kind of like that. Anyway, so 3D, there is no hope. 3D solid, there is no hope. It's too complicated. Nobody can pretty much do it unless you do what are called molecular dynamic simulations. And I mentioned this earlier. Molecular dynamic simulations are studies where you actually uh, take the atoms in a computer, you place the atoms in certain positions, you give them certain initial velocities, you insert atom-atom interaction, maybe according to your Leonard-Jones potential or some other realistic potential that will model that particular material. And then you first can start with a molten version of the system. You turn on temperature. There's a way of doing that. And then you run the equations of motion, Newton's equations, um, in the presence of temperature. There's a way of doing that. These are what molecular dynamics simulations do. And the vast majority of us who look at 2D and 3D systems um, do this using molecular dynamics simulations. Uh, Full disclosure, I personally haven't done simulations since 90s because the simulations were developed from 50s onward. Um, and right now, what it is that you can go to the Sandia National Labs website and just sandia.gov, and you can look for what are called LAMMPS codes, LAMMPS, I think, or I can find out for you. Uh, yeah, I think LAMMPS. Um, right now, they have their own website. Uh, like here, I'll quickly share it with you. Let me share this screen. This is the screen. So this is the way to do it. You can go to this website. It's now called docs.lamps.org. It is a website from Sandia National Labs. And as you can see, LAMP stands for Large Scale Atomic / Molecular Massively Parallel Simulator. So you take an atomic scale, molecular scale system, you insert the potential, and you basically run this code with the right initial conditions, the right temperatures, the right boundary conditions. There's a whole slew of stuff that you have to go through. And essentially, it simulates for you how a three-dimensional or a two-dimensional many-body system might behave. It's pretty sophisticated and it's very, very well checked because it's free and worldwide people use it. So any errors that may be observed are reported. The codes are benchmarked and corrected. And because globally people use the same code for their studies, uh, a tremendous amount of progress has been made. And this has become the way of doing these studies. Uh, One doesn't usually attempt them analytically for reasons that you will see why they are not done analytically anymore. Maybe analytical ways is not the best way, but this is a huge thing. And please, uh, when you find a little bit of time, I strongly, strongly urge you to download this code, look at it. If you can actually run it on your machine, by all means, please do. I mean, back in the 90s, when I last ran it, I actually taught it in over 2 years in classes in second, and there was a third semester StatMech for a while. So I ran it for the students there, and the students did projects. And a couple of those projects actually were published in Physical Review. They became very decent research papers, new, novel problems, and they were constructed using LAMMPS codes. Now, okay, so this is the way you do 2D melting, 3D studies, and so on, which we will not otherwise do. But if you are interested, if you are interested, um, what I can do, what I can try to do, certainly, although I haven't done it in a long time, is to give you a primer on how these simulations are done, because that alone is an art. Um, I'll just set up a few slides if you want. Let me know. I'll have to prepare for it. I haven't done it, like I said, in 30 years. As to how you do this, because this is a skill set that not only is very valuable for you as a student as to how to simulate these systems, it turns out it's extremely valuable when it comes to scientific jobs, because a great deal of the job market still needs uh, you know very skilled materials simulators. Uh, and these material simulations in our days, when I was a kid, used to be done using standardized codes in those days from the big guys, and that's the code I used. Uh, but those codes have now been replaced by these codes in the following way. Those codes actually have been essentially, streamlined, massively parallelized, new, snippets of sort of theories introduced there, new ensembles inserted there. So they have become vastly more capable. So you don't need to mess with those old codes anymore. LAMMPS already gives you a much more a structured way of doing these studies. And that's the reason why, uh, you know, play with it, run a few simulations. A simple simulation would be take sodium atoms. Sodium has Leonard-Jones potential. Take sodium atoms, set it up as a liquid, set it up at a reasonably high temperature, maybe like uh, you know, I don't know, 300 degrees, 400 degrees Kelvin. Sodium is not very stable at room temperature itself, right? So 500 degrees Kelvin. It'll be, if you can run it to equilibrium, it'll be a nice molten sodium you have in your system. And then in very, very small time steps uh, with independent runs, by using the previous run as your input for the next run, you can cool it down and you will see a solid sodium chloride crystal form in front of your eyes. You can just do this exercise to convince yourself how incredibly versatile and capable these codes are. You can actually visualize them. You can calculate susceptibilities, compressibilities. You can calculate dynamical quantities if you want. They're absolutely amazing stuff. It's like a real experiment on the computer of the system that you have made. And yes, they do agree with real experiments because these things are that well known today. That is why it has replaced the urge to do theory like we are doing now. Okay, let's go back to our old thing, our slide where I was going to start. Uh, here. So I want to go back to our lattice problem, but in some detail. So let's just quickly take a look at how this harmonic oscillator chain problem is done in the way I showed you on last Thursday. You first of all set up an infinite harmonic oscillator chain, let's say n oscillators, and n goes to infinity for now. Un of t is the displacement of the nth atom from its equilibrium position. So it's important to keep in mind that we are taking displacement from equilibrium position only as the variable. And then you can set up the equations of motion. In this case, the equations of motion for each n would be as shown, which of course can be further, compactified to this form, the lower form. And this is the normal mode picture because this is the picture that I showed you, if you recall, on Thursday when we were talking about that Florencio and Lee's calculation. So this is your normal mode picture. This is where we start the ball game. Okay. And once you have this thing, you actually solve by the following assumption. You essentially replace the displacement with its Fourier transform. So in this case, you have the normal coordinates, and the Fourier transform of the normal coordinates is what is tied to the displacement. So each displacement now in real space, or displacement dynamics in real space, is replaced by the normal mode dynamics problem. Okay? So, and very, very important for us to keep in mind that this whole game can only be played if we have translation symmetry. If we break translation symmetry, then we are we are not going to be able to do this step this way. The natural basis for the solution is a set of complex exponential waves, and we propose a transformation from the physical coordinates un to the normal coordinates qk using a discrete Fourier transform. So this is a Fourier transform. Now, the equilibrium distance between the atoms in our system is now set to a. So each of these atoms are a apart, and you see that a enters explicitly in the Fourier transform. And then you have this small n, which runs from 1 to n. Here they call it p, but anyway, it's the same thing. Now what we can do is we can set up the equations of motion instead of writing it in terms of un, the displacements, in terms of the qk's. These k's are the modes, okay? These k's are the normal modes. qk, q1, q2, q3, q4, these are the mode numbers, low to high frequency modes. Now, so once you put this qk business in there, the equation of motion begins to look like that. Naturally, as you go to the adjacent sites, you move a site by making it n plus 1, and you to the right, and you move a site to the left by making it n minus 1. And then the site that you chose is n. So therefore, you can now divide through by this e to the ikn, and quickly you find an equation that looks very, very simple. mqk double dot is kqk e to the ik plus e to the minus ik minus 2. Very simple. A standard solid state Kittel chapter 5 kind of stuff that we are doing. Now, this term here is nothing but a cosine k, so you rewrite it in terms of cosine k. And then you observe that 1 minus cosine is a sine square of theta over 2, if this is theta. Then, so because it's 1 minus cos k, you have to put a minus sign. And this then becomes your very simplified equation for each of the k's. And that is what becomes quite trivial to solve. And so you can now construct a description of the Hamiltonian in terms of qk's and qk dots instead of your, or qk's and pk's instead of your displacement and velocity or momentum. So important thing to note is that this equation, of course, is a harmonic oscillator equation, and the omega k turns out to have the structure. So this, as you know, is called dispersion. How omega k varies with k, the wave vector, is dispersion. So this is the dispersion relation. And then you can always return to the displacement coordinates by doing an inverse Fourier transform. So this is the way you do the problem. And that is why the Hamiltonian now can be written instead of n, instead of particle, uh, in terms of modes, the k modes. And of course, if n goes to infinity, the number of modes will also go to infinity. K also will go to infinity. And so it becomes, in terms of the momenta and the position, it's a quadratic Hamiltonian. And in this case, because the qk is tied to a Fourier transform, q star is minus ik, na, whatever. So that's how it is constructed here. So if you actually substitute the qk formula that you have uh, into the UN formula, let's go back to the Hamiltonian, I'll show you. I didn't quite write the Hamiltonian, but if you write in terms of the Hamiltonian, then you will get exactly the Hamiltonian in this form. You'll get sum over n pi squared over 2m plus sum over n again, k over 2, not k over 2 or k over 2, I think. And then un minus 1 whole square. That's your harmonic oscillator Hamiltonian. Here you get the same, but in terms of independent decoupled oscillators. There, the displacements of adjacent particles are linked. So the other way of looking at this treatment, of course, is using phonons in quantum mechanics. So each of these normal modes are phonons, and they carry a momentum of h bar k in the quantum mechanical picture. So I just wanted to kind of, remind you about this treatment. You guys have seen this treatment before, right? Tony, you have seen it, right?
Yes.
Yeah.
Okay. So yeah, I just wanted to make sure that this is not the first time. So now you go. This is what I was showing you on Thursday in the Florencio and Lee paper. They constructed the Hamiltonian like this. I think this is small p, not large p. And they started with the center particle, the zeroth particle, and then n over 2 runs to the left and right. Okay, so that's how the indices are set up the way they are here. It is k over 2, so I was right. And here k is now linked to m omega squared because of what we have just seen. Now, this condition is typical, although it is not really necessary for us. But periodic boundary condition making the chain into a ring is typical. That way it becomes endless. You don't have to worry about the boundaries. But let's not worry about boundaries anyway, because we are going to take n going to infinity. Boundaries can always be very important in many body problems. And this is something that we don't often talk enough about. A problem solution is significantly affected by the boundary conditions, almost always. In fact, you can get novel physics sometimes if you change the boundary conditions. The boundary conditions are very critical. So in this case, just like before, you again write the qj, small qj here, in terms of the capital Q alpha, just the normal mode thing that I showed you, and the pj, small pj, in terms of the capital P alpha. So this is the particle level picture on the left and the mode level picture on the right. And you have the Fourier transform quantity here. And just like before, as I mentioned, Q star of alpha would be Q of minus alpha, P star of alpha, P of minus alpha. And you can write the Hamiltonian in terms of decoupled modes. And you can see the number of modes is n plus 1 because there are n plus 1 particles. So in harmonic systems, the number of particles equals the number of modes. If you have 5 particles, you should have 5 modes. If you have 2 particles, you should have 2 modes. It's very simple that way. By the way, if you add the slightest amount of nonlinearity to the Hamiltonian, in the mode picture, you get an infinite number of modes. Yeah. Even the slightest dose of nonlinearity will take you to infinite number of modes. And I'll return to this point. I'll return to this point, not today, but after a while. So anyway, so omega alpha, just like before, I talked about this dispersion relation. This is the dispersion relation here. So omega alpha squared, this quantity is 4 omega squared sine square pi alpha over n. Alpha is our mode index. N is the number of particles. It tells you, how many of these pieces are being broken up and so on. Now, and you can draw this dispersion relation. It's like, you do omega on the y-axis and alpha along the x-axis, and it's like this sine square plot up to the Brillouin zone, because the system is a periodic system. Now, the results that Florencio and Lee calculated were constructed from a formulation like this. So the velocity, it is called the velocity autocorrelation function. This is the name for it usually. The velocity autocorrelation function, Vjt, Vj0, it turns out to be the scalar product involving P alpha t and P alpha prime in general. It will turn out that because the modes are orthogonal, it will only become P alpha t, P alpha eventually. And small qj is the same thing, but Q alpha t, Q alpha prime. And what is this inner product? Inner product is simply the e to the minus beta h times the two quantities here. So in this case, it will be v square, vt, v0, ensemble average, canonical ensemble average. And z, of course, is your canonical partition function. Now, by the way, dn of x is not just x. Dn of x is dqi dpi. It should be small p here. It's a typo. dqi dpi. Okay, so one more comment I wanted to make here. For most liquids and also solids, the velocity autocorrelation function of a particle, only classical, velocity autocorrelation function of the particle is pretty much the most important quantity you calculate from a non-equilibrium statistical mechanics point of view. Now, you may be wondering, why is this the most important quantity you'll calculate and not the qjt, qj0? The reason is that, again, because of that mother of all truths, experiments. In experiments, when you actually make a measurement of how a particle's velocity is behaving over time, and you do that, let's say, by light scattering, or if you have something else, you do it with neutron scattering, uncharged particle scattering. The information that you get is called the dynamic structure factor, denoted by capital S, and capital S is a function of momentum exchange, K, and of frequency, omega. So let's say you integrate over the momenta involved. So then it becomes S of omega, right? You integrate over the R dependence, position dependence. No real impurities, pristine system, no problem. Our system has enough disorder, no problem. So S of the K or the R part in real space, gone. Then S of omega. This Vj of t, in this case, it's just Jj. The Vj of t, V of 0, the Fourier transform of this is your S of omega. That is why it is so important. It is something that you can directly check. The dynamic structure factor connects with Vj of t, Vj of 0. Now, if you want to measure S of k and omega, then again you have to come back to this fellow here, excepting now, instead of making J and J, you'll make J and J prime. Because J prime minus J is going to be that R. And that R is going to give you the K in S of K omega. So this velocity autocorrelation function is pretty much regarded as important as partition function is in equilibrium problems. Just keep that in mind. It's a very big quantity. Anyway, this is something I've showed you. So the scalar products here are not difficult to do. They're very simple Gaussian integrals, already decoupled integrals in K space. So they're individual integrals, Gaussian integrals, like e to the minus a x squared type integrals. And so they're trivial to do. And you get these answers for f0, f0, and f1, f1. And f2 is 0. You basically have two frequencies. You have a zero frequency and a single frequency. So when you solve the second recurrence relation, you ultimately get a solution for your each of your normal modes P of alpha. And it turns out that it is cosine of omega alpha t P of alpha minus omega alpha sine omega alpha t Q of minus alpha. So P of alpha t P of alpha prime becomes is delta alpha alpha prime. So they have to be, they have to be the same, otherwise it won't work. Cosine of omega alpha t. You can't ask for anything simpler. So ultimately you are just left with one frequency here, and therefore Vj of 0 becomes the sum over all of these modes of the cosine of omega alpha t. Alpha keeps changing as particle keeps changing. And so therefore you can convert this sum when n goes to infinity to an integral. And Vj of t, Vj of 0, kt over m, this n goes away because you're integrating over n here. That n and this n goes away. As n goes to infinity, n plus 1 and n are the same. So all of those are taken care of. And then you get this dx of omega xt, and omega x is your good old dispersion relation. Good old dispersion relation. So this is what's in that paper I gave you, that Florencio and Lee paper. By the way, did I send you that paper? I probably haven't, have I? No. Okay, I'm going to send it to you today. So, so what have we done? What we have done is we have taken a harmonic oscillator chain. We have made it go to infinity. We have replaced the harmonic oscillator chain from real space description to K-space description. And in doing so, we have found that there is a dispersion relation. So this is where we went from real space description to K-space description. This was the real space description here, or here. From here, we went to the K-space description. For that, we took a Fourier transform of the position variables. And then we went to this normal mode variables, thus by doing this Fourier transform. These are your phonons and modes. And then we write the equation of motion in terms of phonons and modes here, which is trivially solvable. And once we put it in this form, we already know that the frequencies are well understood. And that's here, the dispersion relation. And then we start solving the full problem. After we have checked that, we essentially go to this description of the Hamiltonian. We have already done this. And from there, we directly calculate the Vj of t, Vj of 0. All we need to do is calculate this quantity. We already know P of alpha t and Q of alpha t. That is being done here. I didn't write the Q of alpha t part here, but P of alpha t is good enough. So once I know P of alpha t, I can multiply with P of alpha. So I have P of alpha, Q of minus alpha, Q of alpha. And then I have Um, I do the ensemble averages like here. And once I do the ensemble averages, I am able to express the VJT, Vj0 very simply in this form. And once I allow n to go to infinity, then I get this integral, and this integral lends itself to a zeroth order Bessel function. So this becomes your great result for calculating the velocity autocorrelation function. So this result is, by the way, not that old. Okay? This result was first obtained um, in the 1960s, but uh, the diffusion coefficient of the system was first reported in 1983 by Ronald Fox. Ron Fox has passed away. He used to be a professor at Georgia Tech. He was quite a distinguished statistical physicist. But look at the diffusion coefficient calculation. The diffusion coefficient in this approach is simply the time integral of the velocity autocorrelation function. This is also one reason why the velocity autocorrelation function is so important, because it not only allows us to calculate S of k omega and all that, it also allows us to calculate diffusion coefficient. Interestingly, nothing is diffusing. You have a harmonic oscillator chain which is not going anywhere. Right? It's not going anywhere. But when you calculate the diffusion coefficient, funnily, your diffusion coefficient is non-zero. So it tells you that the particles are actually diffusing. Why? Why does it give us this extremely unfriendly result? There's nothing wrong, by the way. That is because, remember I told you that there's a zero frequency mode, there's a regular vibration frequency, and there's a drift that can happen. That drift is possible. So in other words, you can take a chain, infinite or otherwise, and this chain has every right to drift along wherever it wants in space without any change. So that diffusion is still possible. And it is that diffusion that actually gives you this vector here. It's basically the drift. So how do you get out of drift? And that is discussed in that Florencio and Lee paper. I didn't show it here. The way you get out of the drift is you take the last particles as n goes to infinity and tie them to two walls, two boundaries. So then the last particles are actually anchored. And the moment you anchor them, the thing cannot drift. And if the thing cannot drift, what do you expect? Well, your diffusion coefficient looks a lot more complicated, but if you go through the calculation, you'll find that it vanishes, as it should. So that also is another reason that the diffusion coefficient here is finite, because the system can drift. When you try doing molecular dynamics, you might be encountering calculation in an ensemble where, let's say, temperature is constant that you're setting, system volume is constant you're setting, number of particles fixed you're setting is also some number. But you will find in addition it is written that center of mass momentum is zero. And they will say the ensemble is TVN, P equal to zero. Or TVNP, P being the center of mass momentum. In this case, the center of mass momentum was not set to zero. It could drift at uniform velocity. There's no force. Okay, that's the physics. But in molecular dynamics, the same thing happens. You are integrating equations of motion, there is always a constant tagging along. That constant is tied to the drift. So you have to forcibly, as you loop around in time, the calculations, you have to forcibly center your system at the center of mass being zero of your coordinates. Now, back in the day when I learned, these codes were not standardized. And so I had a code. That code came from Anis Rahman, and I mentioned the name. You might remember Anis Rahman was one of the founding fathers of molecular dynamics that we do today. In fact, all these codes came from Anis Rahman's code. So I had Anis's code because Anis was a collaborator of mine, professor. Uh, and I was trying to do a certain calculation that was part of a homework in a course in a sodium system, Leonard Jones sodium atom system. I don't know how many atoms I had, not very many. I had about 256 atoms or something. The standard number, it has been powers of 2, that's why it was 256. And I had submitted a run for a certain calculation at night. Next morning, I came and logged on to my mainframe, and my system was not there. My code was there. I could clearly see that I had a lot of data. I could not see my system. My system was completely gone and missing. And so, you guess what happened? The system drifted off. That's what happened. So all night as it ran, the system was drifting by a fixed amount every, you know, several 100,000 time steps. So in the morning, when I came back and the run was finished, my system was not where it should have been. It was very far away. So I had to go find it actually. I had to type in what kind of coordinates it was. And sure enough, the run was perfectly done, but the system had run away. So that's how the hard way I learned that you have to zero the center of momentum. So ever since then, whatever calculation I've done, I make sure my center is properly taken care of. All right.
Very, very bad joke, by the way.
Exactly. So it was a horrible job. It did, and it gave me a heart attack because it was a big run. I had done all the tests. I knew things were running, and I was going to make this big run, and then this happened. All right. So let me go back and beat up on this system for a few seconds more before I let it go. You see, the biggest problem that we have here is that this is a pristine system. Every mass is m, every spring constant is k, endless system, pristine system. However, the most interesting systems in the world are not pristine systems. Most interesting systems in the world have impurities, defects, boundaries, all kinds of stuff. As I pointed out, that's where interesting physics comes. I'm not saying this is not interesting. I'm saying even more interesting physics comes there. But this normal mode analysis based approach has a severe limitation. It simply cannot handle anything that breaks translation invariance. Okay. So we now need to find a way where you can deal with the physics in the absence of translation invariance. Now, nature is like a bratish child. That's like one face of nature, because nature will make your life difficult no matter what you try. So while this approach has so many goodies going with it, when you go to another approach where you can take impurities and all these, complexities into account, let's say that works, and indeed what I'll show will work, but you will find that you are paying a price somewhere else. So this is the reason why that whenever you do any subject, statistical physics or otherwise, you end up doing that subject well when you learn multiple methods, multiple ways of approaching a problem, because every way comes with its own bag of problems. So just like translation invariance has its bag of problems with regard to impurities, this approach, the continued fraction approach, as we'll now get into, has its own problems. It is very friendly for calculating autocorrelation functions, but it is very unfriendly in terms of visualizing what's happening to the system in real space because it doesn't work in real space. It takes you to a Hilbert space. And that Hilbert space analysis gets you, it's like a flyover to the relaxation function. But what you are flying over, all the details and all the jazz underneath your flyover is simply not captured. Or it is captured in such an abstruse way that you can't get it. This is the price you pay. You get to the end point, get to the big goal, but you miss all the physics that you could have seen if you could actually observe the system in real time in the laboratory. That you can't get. So let's go back to our Hamiltonian. This is our Hamiltonian. And in this system, the way it is set up, you can see that the mass is not homogeneous. The mass has an MI. So the most general system that I know that has been really studied in great detail in terms of exact solutions is a system where you have an impurity at O here, and otherwise it is a diatomic system. So this particle has a mass M1 here, and the black particle has a mass M2 here, and this shaded particle at O has a mass M0 here. This has periodic boundary condition. As you can see, there are only 8 particles, and the way it is set up, P of minus m, so momentum of minus m, that will be this particle here, is also the momentum of plus m, because the right side is numbered with pluses, left side is numbered with minuses, just so that some symmetry can be invoked in the calculations. Very standard trick. Further, the ratio of mass m1 here is called m only, over m naught is denoted by lambda. Now, for now, I will actually turn off M2. I'll make M2 equal to M1. And I'll just keep in general an impurity M0. And I'll either turn M0 on to M0, which means a system with a single impurity, or I'll make M0 to M1 or M, in which case I fall back to my previous case of pristine system, but not now being done in real space. And we are also cognizant that we are looking at cases where n is an even number. But that doesn't really change physics all that much because we are typically interested in large n's anyway. So this particular study that I'm going to tell you has not been, I think it has been published only recently, but the study was really kind of weaved by this gentleman here, Mingbao Yu. Professor Yu is now in his very much in his mid to late 80s, but he was this Chinese professor who was visiting my advisor's research group when I was a student, and he stayed back actually. He stayed back, but he turned out to be quite incredible in doing this kind of research. So I'm going to spend time talking about some of his work as a way to deep dive into how to do these problems because this is really it's very cool. The fact that you can do it the way he does it is very cool. Okay. Now, you might be thinking that, oh, it's a harmonic oscillator system. How bad can it be? Why are you spending so much time on it? Why don't you move on to more sexy stuff? Let me tell you how sexy this is. It's important to put that in context. You remember Einstein? Now that's pretty sexy usually. So Einstein constructed Brownian motions description. And that basic idea of Einstein and people like Stokes and all, where you have a heavy particle. This heavy particle is moving in an environment of smaller particles. And these smaller particles beat up on the heavy particle, right? Because They're continuously colliding at high frequency with the heavy particle. The heavy particle can't really sense all the small particles other than some kind of a drag or a viscous force. So all these small particles collectively slow the heavy particle down. But the heavy particle doesn't really have a very good memory of these individual collisions of small particles. This picture, nothing wrong with this picture. This picture is what led to the concept of Brownian motion, number one. Number two, when physicists started studying the dynamics of the harmonic oscillator chain as an elementary problem that needed to be mastered and wanted to solve it rigorously, that drive began in the 1950s and early 60s. And one of the problems that was studied was you take a harmonic oscillator chain with an impurity, obviously now break translation invariant, so that there's a huge price to pay because of that. And you make that impurity a large particle, a large mass. So then, in principle, if you have an infinite number of other masses and a large mass, as this large mass moves to the right and left, it should experience the kind of motion that is, if not the same, reminiscent of Brownian motion. Brownian motion is in 3D, this is in 1D, but it should be similar. That was the idea. So when this problem was attempted, the first many people essentially solved this problem with the assumption that Brownian motion will work. In other words, the dynamics of this large particle would reveal Brownian motion-like dynamics. That was the assumption. However, there was a need to prove it, that whether that is indeed true. And the first person who accomplished this proof wrote a series of 4 back-to-back papers, each about 15 to 30 pages long. Yes. And these papers appeared in, if I recall correctly, in 1 or 2 volumes of Physica A. At that time, it was just Physica, not Physica A. Now it is Physica A, B, C, D, there are all these. But back in the early 1960s, mid 1960s, the journal used to be called Physica. It was a Dutch physical review, Dutch equivalent of physical review. And this gentleman, Ullersma, wrote these 4 back-to-back papers. And in these 4 back-to-back papers, Ullersma studied the harmonic oscillator problem in all its glory. He studied the pristine monodispersed chain. He studied the diatomic chain. He studied the single impurity chain. He studied all of them. What is amazing is that Ullersma got the physics right. And reason why it is amazing is because the physics of this problem turns out to be hellishly bad. It is hellishly bad. And Ullersma did that without making any mistakes on his own back in the day. Now, Ullersma used his own technique for it. I'm not going to go to Ullersma's technique. I could have, but I chose not to because the continued fraction technique is actually very general and it gets to Ullersma's results fine. Not only that, it gets to all of the other results within one umbrella. Price paid, it's a flyover from the perturbation to the relaxation function. Everything in the middle, the detail of the stuff, you don't get to quite figure out from the calculations that you do, because it is done in Hilbert space. It is not done in real space. So the first report on this study of just the full harmonic oscillator chain with a single impurity was in this paper And this is a journal that is mostly used by laser science people, this Journal of Luminescence. It's actually a very well-known journal, but it's a journal for people who are from laser science. There was a conference and it was part of that report. This paper is highly skimpy. It doesn't tell you very much. But let me just go to the next slide. The way this gentleman, Professor Yu, approached this problem was he first took a 2-particle chain, and then he took a 4-particle chain, and a 6-particle chain, an 8-particle chain, and a 10-particle chain, and a 12-particle chain. He kept on doing it. So let's look at his 2-particle chain problem. So 2-particle chain problem, basically he had one impurity and one mass. So M0 and M were the two that he had. In this case, as you can see, lambda is 1. So M0 is set equal to M in this particular case. But he studied the general case. And there was an F0, which was momentum, P0, F1 and F2, two other, and ultimately it closed up. So F3 onward, everything became 0. The capital D is nothing but the deltas that we have seen. Here it's written as D. So delta 3, delta 4, delta 5, all are 0. And Hilbert space dimension came out to 3 in this problem. Number of particles was 2. M was equal to M0. And the relaxation essentially came out to this 1/2 into 1 plus cos 2 omega t. So one is a drift mode and one is a mode like this. Drift mode is this and this. So this is the 2 omega, small omega, k over m to the half. Very simple problem. Anybody can do this problem. N equal to 4. When he attempted that, he found that the Hilbert space now was a 4-dimensional space. And these actually are the norms. These are the norm squared. So this is F0 squared, F1 squared, F2 squared, F3 squared. And let's see, is that the norm or is that the delta? I think it's delta 1, delta 2, delta 3, delta 4. Yeah, that's what it is. And as you can see, the 4-particle system has 2 frequencies, omega t, 2 omega t, and a square root of omega t. And then it has a 0 frequency mode, omega equal to 0. I'm just giving you results first. I'm going to show you how this comes about after that. When n equal to 6, he could only go up to F6, and after that, F7 onward, everything was 0. So delta 1, delta 2, delta 3, delta 4, delta 5, delta 6. Do you see a pattern? 2k over m, 2k over m. 2k over m, k over m, k over m, 2k over m. 2k over m, sorry, 2k over m, k over m, oops. K over m, k over m, k over m, k over m, 2k over m. So it's always ending with 2k over m, beginning with 2k over m. 2k over m is coming as the series opens and closes. That is what the pattern reveals. So now you can extrapolate that as n goes to infinity, you will basically go from this pattern, lambda is 1 here, k over m is set to 1, to this pattern where it never closes, because n has already gone to infinity, right? So how will it close? That's 2, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So now you can trivially solve the equation of the continued fraction, because it is a0 of z, 1 over z plus 2 over z plus 1 over z plus 1 over z plus 1 over z plus 1 over z goes down. And if you want to put back the impurity, you don't have to do any more work. Just stick the lambda in here. That's it. because the first one is tied to M0. Nobody else is tied to M0. So the effect of impurity over here is quite simple, but it's quite dramatic. The first level carries the information about the impurity because the impurity is being perturbed. So if you're studying the impurity plays an extremely important role. Actually, if you have a continued fraction, then the most, uh, you know, lowest order deltas tend to be some of the most important contributors to the structure of the continued fraction. A delta very deep down will still have a role, but a weaker role than a delta very high up. So if delta 1 is getting affected, it immediately tells you that your deltas are getting big time affected by the impurity, as it should be, because this impurity is the one that is the connection to Einstein's problem, as it should be. So what I'm saying is that this particular approach, which looked so crazy to begin with, that you make this ring and you do it for two particle, 4 particle, 6 particle, 8 particle, 10 particle, 12 particle. The idea is that by induction, you are using the oldest trick in the bag for mathematicians. You are by induction figuring out what is the structure of the infinite system. The whole game is to do it by induction. Okay. Uh, so as I said, in general, for n going to infinity, this is what you end up getting with some simplification. K over m has been set to 1. That's why it's a 4. It's actually 4 K over m. I think is the formula. I have it somewhere. I'll show you. It will come at some point probably. And this lambda is m over m0. So if m0 is big, lambda is less than 1. If m0 is small, lambda is greater than 1. So you see that's why lambda equal to 1, lambda equal to 0, and lambda equal to half. They're important limits in this problem. So I decided that I was going to try to do it numerically to see if it gives the right result. And I had a very interesting experience. 3 times I got the right result, and about 2 times I got the wrong result. And I was wondering why, and then I found out that the slightest mistyping here, actually I was using a slightly different format for it, same expression, a little bit more complicated format for it, where I had a lambda downstairs and a lambda upstairs and so on. The slightest screw up in the formula creates a havoc of a difference, number one. It shouldn't, but it does in this case. But even if I didn't screw up, the very instructions I put down as I was trying to solve it numerically can have an effect. So it's an extremely sensitive integral. And the reason is this integral is done over several Riemann sheets. It actually has branch cuts all over the place. And that is exactly the reason why Ullersma was the first one to get it right, because Ullersma treated the branch cuts properly. In the past, everybody tried before Ullersma and everybody who tried after Ullersma, without essentially following Ullersma, made a mistake. So 95% of the papers that have been published by statistical physicists on the Brownian motion problem in one dimension are wrong. And among them are very, very famous people in this field. Okay, you have heard of Vera Rubin. There's the Vera Rubin Observatory up now. So Vera Rubin's husband was Bob Rubin. He was a statistical physicist, a very well-known one. And Bob Rubin used to work at NIST, National Institute of Standards and Technology. I've actually met Bob Rubin. I've corresponded with him because I was very interested in this problem. And Bob Rubin actually worked on this problem. And one of his life's mistakes was this integral. He messed up this integral because he missed the branch cut. And he equated the solution to Einstein's solution, whereas it was not. Because if you make the mistake, you get Einstein's solution. If you don't get the mistake, you get this solution that I show here. That's why it's so critical. And just look at this solution. It's an infinite series of polynomials. In this case, infinite series of Bessel functions. It's just one nasty solution. Now, so this solution becomes a J0 of t if you take away the lambda. So if you set lambda to 1, this thing essentially goes over to a J0 of t. So now you see, if you plot it, it got cut off a little bit, but this is how the Bessel function solution looks. It's highly oscillatory, and you can see that this is for lambda equal to 1. Impurity has been turned off. This kind of a slow decay that you see of the peaks in the relaxation behavior is actually an algebraic decay. It's a t to some power, t to the minus some power. Typically, I think minus 3/2 power in this case. Could be minus half. I have to check that. You can look at Abramowitz and Stegan's book and you will see that it's nicely explained there. So now let us look at it when lambda is 0.1. When lambda is 0.1, mind you, m0 is 10, m is 1. Because it is 1 over 10, right? 0.1. Now you see the same A0 of t looks like an exponential decay, which is the hallmark of Brownian problem. So there is a vestige of Brownian-like behavior coming in, but it is not Brownian. It's actually a Bessel function behavior. And this behavior is correctly being predicted here by the continued traction approach that Professor Yu did, and also agrees with Ullersma's results. And actually, had Bob Rubin seen this, Bob Rubin would have been very happy because Bob Rubin would have said, hey, Surajit, you just don't have exponential behavior here, but that you don't expect anyway because of time reversal invariance. You see, I told you, you have exponential decay. Problem is that this is not exponential decay. It is actually power law decay, but the power law is small. In fact, my answer to Bob would have been, and in fact, I sent him this note when he was alive. He was still active when I wrote the next paper in the next page in 94. I showed Bob that see, this looks like an exponential decay, but it turns out that if you look at it in a much finer scale, and this of course is 0.00005, so 10,000 fold finer scale, you actually have hidden oscillations here decaying over the same time period. These are the hidden oscillations decaying. So that is why it is a Bessel function decay. And that is why this is different from what Einstein had predicted. It is not the same. So one-dimensional heavy mass physics turns out to be different from Einstein's result. And that shouldn't be a surprise. Einstein didn't make it a 1D problem. Einstein basically made a 3D problem. So, this is a beautiful illustration of how you can use a broadly framed approach for resolving what has been an outstanding question. Had you done it purely numerically, also you would have gotten the right result, of course. But this, we got the analytic form. So therefore, it's good. It's good to have an analytic form. You can do this diatomic chain with an impurity problem. I'm going to show it to you, but we are out of time now. But one of the things I want to illustrate to you is that I think of these set of slides that I'll bring up on Thursday as the quote unquote underbelly of how this works. Because when you look at the, pretty results like this, for example, it is so easy to forget what level of labor was involved in getting this pattern and in discovering that this problem can be exactly solved. And then the next stumbling block is just the branch cut physics. And if you can do that, you get the right form. The amount of work that has gone into this is something that is worth appreciating because that's what is required. Vivek had mentioned, and I think Tony also was mentioning that the algebra is very daunting, right? The thing is, if you ask, Doreen is my high energy theorist colleague in Buffalo. Uh, you don't know Doreen, Vivek, but if you ask Doreen about what she does, and Doreen and I had a nice conversation on this many years ago when she had come, relatively new faculty member. And Doreen was telling me how her time is spent in doing so and so order calculations for 6, 7 months. Uh, that's what she does. She does these higher order correction calculations in QCD. Now, and the reason why we used to compare notes and chat is because I also know how difficult it is to get to these high order terms and the physics. I mean, the reason why Feynman ultimately got the Nobel Prize was because he did crazy orders of algebra to show that his way of working these uh, QED calculations was working, right? I mean, had he not done to that level, he wouldn't have gotten the precision and hence the insight. So this problem of doing this calculation is based upon so many subtle observations and tricks that it's worth noting. And the biggest part of it is surely the nomenclature. So I'll take you through that a little bit. I'll show you how the Liouville operator looks like once you frame it. This is actually the structure of the Liouville operator. I'll show you what kind of structure emerges of the F's and the norms, F nu squares, or the deltas in general. And I'll also show you how you calculate the scalar products and partition functions purely geometrically. Because once you do the difficult integrals, you use this quote unquote renormalization trick to reduce the entire calculation beyond a point into primarily doing uh, observation based analysis because you know the answer, what's going to happen without doing the calculation. You have done the underbelly part of the problem. And that leads to beautiful results without doing. Look at this result at the bottom. This result is the calculation, is getting to the final stage of calculation of a partition function. Just that result. And look at the sizes of these integrals. So the reduction from this to that can be done. And because this was done, this beautiful expressions for partition functions could be obtained. Now, if you put it on a machine, the machine will give you a divergent answer because this V is a volume that goes to infinity. But infinity has been suppressed with the word V because V eventually cancels out in all physical quantities. Okay. So how else would you know how it works if you don't get it to this level? And that's the beauty of some of these studies. So I want to show you this diagrammatic way and how it works a little bit. So we'll discuss that on Thursday. So this is how much of detail I have that I was going to get to. But let us